All right, we have achieved three learning objectives in the first three videos. So now we're going to try to define and differentiate exponential functions having bases other than the number e. So let's get started. So we know that the base of the natural exponential function is e. So we have once we have e to the x, this number is e, and that's the base of the exponential function here. So and what happens if you change this base to another number, a? And let's say like a is a positive real number, not necessarily equal to 1, because 1 to the x is going to be 1, so that's not interesting. So let's assume that a is not 1. Then to be able to take the derivative of a to the x in the next few slides, you will see that we're going to redefine a to the x as e to the ln a times x, and take this as the definition of a to the power of x. And the same story goes on with the logarithmic functions having bases other than e. So let's say like we consider a log function coming with base a. And by the way, if the base is e, we call it natural log function, and there's a special name for that, ln x. Okay, so what we can do here is that we can redefine this function with the use of the natural log function. In fact, logarithm x with the base a is the quotient of ln x and ln a. So take this as the definition of the logarithmic function x with the base a. So now by redefining a to the x and logarithmic function x with base a, so we can talk about the derivatives of each function. Let me just show you how we took care of the derivative of a to the x. So d dx of a to the x is equal to d dx of a to the ln a times x. Okay, so now to take care of the derivative of this exponential function, we can use the chain rule. And the chain rule states that the derivative of this function is the same function times the derivative of the power. But ln a is just a number, so it's a constant. By using the constant multiple rule, the derivative of the top is ln a. All right, since we know that e to the ln a x is just the other name of a to the x, so this derivative is reduced down to a to the x ln a, or ln a times a to the x, and that's exactly what we have here. And let's apply the same strategy for taking the derivative of logarithmic function x with base a. So we know that a logarithmic function with base a can be rewritten as ln x over ln a. All right, well, ln a is a constant, so we can pull it out of the derivative. And we know that ln x has the derivative 1 over x, so that we have 1 over ln a times x, and that's exactly what we have here. And now we can use the chain rule to take care of the derivatives of a raised to a power of a function of x. So the derivative of that goes exactly the same as this one, but then we have to multiply everything by the derivative of the power, which is du over dx. And the same thing here. The dx of logarithmic u with the base a is equal to, so we just copy that down here, 1 over ln a u times the derivative of u with respect to x. All right, let's go through this example to apply the rules that we have just learned. So the first one is d dx of 2 to the power of x, and this is an exponential function with base 2, and we know that the derivative of this function is 2 to the x times ln 2 by using the rule that we just learned. And the second example is d dx of 2 to the power of 3x. So this time the power is a function of x. So the derivative of that is, well, ln 2 times 2 to the 3x. So far, everything is good. And we have to multiply this by the derivative of the power, which is 3. So bringing all together takes you to 3 ln 2 e to the 3x. All right, the next example is a logarithm cosine x with the base 10. We can rewrite this as ln cosine x over ln 10, and the derivative of ln cosine x is the derivative of the inner part divided by cosine x. Well, the derivative of cosine x, which is the inner part, is negative sine x. So here we go, divided by cosine x, and we still have ln 10. Bringing all these together and using the definition of tangent, which is sine over cosine, we can simplify the final expression to minus 1 over ln 10 tan x. All right, our final example is taking the derivative of this function, but before we take the derivative of that function, we use the property of log functions. So logarithm of quotients can be written as the logarithm of, let me just write it here, logarithm with the same base of the top minus a logarithm with the same base of the bottom. So you have x plus 5. We also use another property of log, which is this term can be written as x to the power of 1/2. We can always pull the power out of the log, so we can write that as 1/2 x with the same base 3 minus log 3x plus 5, and this is exactly what we have here. Once we put this function in this form, we can take care of the derivatives individually. So let's just do that in the next slide. Here we go. So now we're taking the derivative here. So let's see what we have. So first off, the derivative of log 3x is, well, since log 3x is ln x over ln 3, the derivative of that is 1 over x ln 3, and we have carried forward the factor 1/2 as well. And the same thing here. This is ln x plus 5 divided by ln 3, and ln x plus 5 has the derivative 1 over x plus 5. Here we go. This is the final form of the derivative of y prime. In fact, you can simplify this further by pulling out ln 3. Now let's just do it together. 1 over ln 3, 1 over 2x minus 1 over x plus 5. And you can find a common denominator to put the difference of two quotients here in one quotient, and that I'm going to skip, but you should do it by yourself. And here's the final form of the derivative of this log function provided us in the beginning, right here. My final slide is all about listing out the rules that we have learned so far. So you have the constant rule, power rule, constant multiple rule, sum or difference rule, product rule, quotient rule, and the rules that we learned today, chain rule, general power rule, and derivatives of trig functions and the derivatives of exponential and logarithmic functions. Please have all copied in one slide somewhere, because you may refer back to this slide when you go through your homework problems. All right, this is the end of the video. Thanks for watching. I'll see you in another video.